Right, in these last set of inverse trig problems, we're going to be combining all 6 basic trig functions with inverse functions. And we're going to be mixing them, so we're not just working with sine and inverse cosine or cosine and inverse cosine. We'll have a healthy mix of all 6 trig functions in there. So on this first one, problem 37, we're trying to get the cosecant of the arc cosine of negative root 3 over 2. So keep in mind that anytime we take the inverse cosine or the inverse sine or the inverse tangent of any number, the result that we get is an angle. So really, I'm just taking the cosecant of some angle. And that inside looks to be solvable. Since we've already looked at all of the inverse trig values for unit circle numbers, we know that the arc cosine of negative root 3 over 2 is 5 pi over 6. And once I know that, then I can just take the cosecant of 5 pi over 6 and get 2. Since the sine value of 5 pi over 6 would be 1/2, and cosecant is just the reciprocal of that, so 2 over 1. Next, we'll look at the cotangent of the cosine inverse of 1/2. But we can start by getting the cosine inverse of 1/2. It's a positive value, so we know it should be in the first quadrant. That'll be pi over 3. And then we want the cotangent of pi over 3, which is root 3 over 3. Moving that along, we'll look at the secant of the arctangent of negative root 3 over 3. So the inverse tangent of negative root 3 over 3 should be negative pi over 6, since we're heading into that negative 4th quadrant. And then we just need the secant value at negative pi over 6. That's in the 4th quadrant where secant is positive, so this should come out to a positive number. And we should end up with 2 root 3 over 3. Since the cosine value at negative pi over 6 is going to be root 3 over 2, the reciprocal of that is 2 over root 3, or 2 root 3 over 3 if we rationalize. Next, we're on to the sine inverse of the cosine of 5 pi over 4. But that's just going to be a unit circle problem first, since we know that the cosine of 5 pi over 4 should be negative root 2 over 2. So we can just get that value off of the unit circle. And then take the sine inverse of negative root 2 over 2, which should come out to negative pi over 4. Since we know we're looking at a pi over 4 class of angle, and we need the one that's in the negative 4th quadrant to match sine inverse. Right. In 41, we have the cosine inverse of the tangent of pi over 4, which means I'll be looking at the cosine inverse of 1, since the tangent of pi over 4 is 1. And then I can go to my cosine inverse values. So I'm looking for an angle that has a cosine value of 1, which happens at 0 radians. So in those first few problems, we just looked at unit circle values when we're combining these functions. And so far, those aren't too tricky. But we could end up with an inverse trig function of some number that we don't recognize from the unit circle, as is the case with 42. I want the cosecant of the tangent inverse of 6 over 1. Or well, it just says 6, but I'm going to call it 6 over 1. Mild spoiler alert. In that case, we can go back to what we learned all the way in worksheet 4, where we were looking at reference angles and reference triangles, to construct a reference angle for the tangent inverse of 6. Since keeping in mind that anytime I have an inverse function, the solution to that is just an angle. In this case, I'm going to call it alpha, which means I can construct a reference angle or a reference triangle for alpha. And since I'm taking the tangent inverse of a positive number, I should be in quadrant 1, which is why I've put my reference triangle in quadrant 1. And that's a tangent value of 6, which means my opposite over my adjacent side should be 6 and 1. So that leaves a missing hypotenuse that we'll need to solve for. So 1 squared plus 6 squared is equal to h squared, meaning that 37 is h squared, so our hypotenuse must be the square root of 37. Now that I have my reference triangle complete, I just need to come back to the initial problem, which was getting the cosecant of my angle alpha. And so I can go to that reference triangle and just get the hypotenuse divided by the opposite side. So square root 37 divided by 6. And that should be my solution, root 37 over 6. So we'll look at doing that process a few times. This time we've got the sine of the cosine inverse of 3 over 5. Again, I'll call that angle alpha. 3 over 5 is positive, which means this is again located in quadrant 1. And cosine is adjacent over hypotenuse, so 3 and 5 respectively. Then we'll need to solve for the missing side, which I'll call y. So 3 squared plus y squared is 5 squared, giving us that y squared is equal to 16. So y is plus or minus 4. And because this is in the first quadrant, we'll need to be taking that positive value. So that opposite side ought to be 4. Finally, we just need to come back to solving that initial problem, which was the sine of this angle alpha. And sine is opposite over hypotenuse, so 4 over 5. Right. Into problem 44, the tangent of the arc cosine of negative 4 over 7. So now we're getting into negative angles and the reference angles that go with them. So I have the inverse cosine of a negative angle, which means that this must be in quadrant 2 based on the restrictions for cosine inverse, which is why I've drawn this reference triangle in quadrant 2. I'll label that angle alpha, which should be that angle there measured from standard position. And I'll put down what I know. So negative 4 over 7 should be equal to the adjacent side over the hypotenuse. So negative 4 on the adjacent side, 7 on the hypotenuse. and another missing side, which I'll call y again. So I'm looking at 4 squared plus y squared is equal to 7 squared, meaning that y squared should be equal to 49 minus 16, which should be 33, which means that y is either positive or negative root 33. Now, come back to what we know about our quadrant. We were in quadrant 2, and in that quadrant, we have negative x values and positive y values, which means I should choose the positive square root 33 out of my plus and minus options from a moment ago. So square root 33, that opposite side. Come back to answer the original question. I want the tangent of alpha, and tangent is opposite over adjacent. So we should be looking at negative square root 33 over 4. Right, on to 45. This time my angle alpha is going to be the sine inverse of negative 3 over 8. And since I'm taking the sine inverse of a negative number, I must be in quadrant 4. So my adjacent side should be negative 3, while my hypotenuse is 8. So this time I'll call my missing side x. X squared plus 3 squared is equal to 8 squared, which means that x squared is 64 minus 9, or 55. So x is plus or minus the square root of 55. Come back to the quadrant. Specifically, this time it's quadrant 4. And in quadrant 4, we have negative y values, but positive x values, because we're on the right half of the coordinate plane. So x should be positive 55, positive square root 55. One thing to point out, if you'll notice, when I wrote out the Pythagorean theorem, I used x squared plus 3 squared equals 8 squared, even though my opposite side was negative 3. And the reason I did that is because anytime I use the Pythagorean theorem, I'm going to be squaring each individual number. And since a square function will always get rid of any negatives, it doesn't actually matter if I include that negative in the 3, because I know it's going to be squared away. Also, I should have labeled my angle alpha at the beginning, so I'll do that now. Alpha is that little angle right there. And this time, measuring alpha in standard position, I do know that it's going to come down from that positive x-axis because it's the sine inverse of some number, which means that it's going to be a negative angle. So alpha will be measured backwards in this case. But enough about all of that. Let's actually answer the question. I wanted the secant of this angle alpha. And secant is hypotenuse over adjacent, so 8 over the square root of 55. Or if we're rationalizing this, 8 root 55 divided by 55. In problem 46, this time I have the tangent inverse of a negative number, which means that I will again be in quadrant 4. So alpha is going to be this angle, again measured backwards from that positive x-axis, and tangent is opposite over adjacent. So 8 should be the opposite side, 15 is the adjacent side, and then I have a negative to put somewhere. And because this is in the 4th quadrant, that negative should go on the opposite side. So it'll be -8 and +15 with a missing hypotenuse. So we'll solve for that. So h squared is 8 squared plus 15 squared, meaning that h squared is 64 plus 225, which is 289. And if we take the square root of 289, we should get 17. Notice I didn't include a plus or minus this time because I know that a hypotenuse is always positive. So there's no question on whether that should be a positive or a negative number. It's a hypotenuse, so it must be positive. All right, then we'll come back and answer that question. I was hoping to get the cosine of our angle alpha. And looking at this triangle, cosine, of course, being adjacent over hypotenuse, this must be 15 divided by 17. All right, and then 47, we get a word problem. So suppose 2 flagpoles are 50 feet apart. One pole is 60 feet tall, the other is 40 feet tall. Find the angle of depression of the top of the shorter pole from the top of the taller pole. So I've already drawn a diagram for us, so we'll just need to put the appropriate labels on here. So starting with what we know, these 2 poles are 50 feet apart. So this distance down here along the ground should be 50 feet. Next, I know that I have 2 poles. One is 60 feet tall, the other is 40 feet tall. So I'll label my tall pole to be 60 feet, while my shorter pole is 40 feet. Lastly, in just the construction of this diagram, I'm going to want to label the angle of elevation. Or sorry, the angle of depression. Because we're asking for the angle of depression from the taller pole to the top of the shorter pole. Which means I'll need a line that connects the top of the tall pole to the top of the short pole. So I'll bring up my ruler and sketch that line. If I've drawn this to scale, it looks like that angle of depression should be about 23 degrees. So we'll see how good my sketching ability is. So here's that line that connects the top of the taller pole to the top of the shorter pole, and I wanted to label the angle of depression that goes from the taller pole to the shorter pole, which means I am looking at this angle right here. I'm going to call it theta. So now I have everything I need to solve for theta. I just need to do a couple of quick calculations first. So I know the distance between those 2 poles is 50 feet. I wrote that down at the bottom. But that also means that the horizontal line that connects the top of the taller pole to the vertical line that passes through the shorter pole, this distance should also be 50 feet because that bottom is 50 feet. So that seems perfectly reasonable. Then for the rest of that triangle that I've constructed up there, I'm told that the tall pole is 60 feet and the shorter pole is 40 feet, but I'm really interested in the difference between those 2 heights. And as it happens, that's going to be 20, right? There's 20 feet between, there's 20 feet of difference between the taller pole and the shorter pole. So I now have a triangle that connects the top of the taller pole to the top of the shorter pole, and also has an opposite side and an adjacent side, since this is a right triangle. So I have an opposite side of 20 and an adjacent side of 50 based on how I labeled my angle of depression. So I should be able to use a trig function to relate all of those. Namely, my angle theta should somehow be related to the opposite side and the adjacent side, which means I'm interested probably in a tangent function. But since I'm looking to solve for the angle rather than solving for one of the missing sides, I'm going to end up needing an inverse trig function, since anytime I use an inverse trig function, my resulting answer should be an angle. So I should end up here with theta being equal to the tangent inverse of my opposite side over my adjacent side. That opposite side is 20, that adjacent side is 50. From there, I can plug that into a calculator. If you're using a graphing calculator, make sure that you are in degree mode, because we'll look to get this angle in degrees. And when I plugged it in, I got 21.8 degrees. So my diagram was actually pretty close to scale. Not too bad. It's off by just a little over a degree, maybe. Not too shabby. Cool, and that's the end of worksheet 9.